these two pen again. This one comes, collides with this, and they both separate, so they don't stick together. And we'll be going through a topic known as linear momentum. And linear momentum, under linear momentum, I will say that firstly, that momentum is the measure of the velocity that a mass possesses. So I say momentum is the measure of the velocity that a mass possesses. So we can say that momentum is equal to mass times velocity. So we said momentum is the measure of the mass that a body possesses, or sorry, the measure of the velocity that a body possesses. So say momentum is mass times velocity. So momentum is equal to, the unit of mass is kilogram, and the unit of velocity is meter per second. So the unit of momentum is kilogram meter per second. So kilogram meter per second. That's the first part. Then also we have that force is equal to mass times acceleration. So we have force equal to mass times acceleration. So we have that force is equal to ma, and we know that mass is kilogram, then acceleration is meter per second square. So the unit of force is either kilogram meter per second square or Newton. So the unit of force is either kilogram meter per second square or Newton. So these are the units of force. The unit of force is either kilogram meter per second square or Newton. Now, apart from this aspect, momentum, force, we also have another part called impulse. Impulse, which is the product of force and time. So force times time, and force is Ft. So force is force times time. So the unit of force is Newton. The unit of time is seconds. So the unit of impulse is Newton seconds. So let's take note. We have the unit of impulse, Newton seconds, or it can also be, force already is kilogram meter per second square times seconds. So seconds will cancel seconds. We have that the unit of impulse is equal to kilogram meter per seconds. Almost the same unit with momentum, kilogram meter per seconds. Impulse is also kilogram meter per seconds. So we'll go to Newton's laws. We have Newton's laws of momentum, Newton's laws of momentum. The first one says that a body at rest will remain at rest, while a body in motion will remain in motion unless it is acted upon by an external force. So we can say that a body at rest, it will remain at what? Remain at rest, while a body in motion, will what? Remain in motion. So we have this, body at rest will remain at rest, while a body in motion will remain in motion unless it is acted upon or by what? An external force. And that external force can be different forces, it can be friction, it can be of any type of force. So body at rest will remain at rest, the body in motion will remain in motion unless it is acted upon by an external force. And that's why you observe that when you are in a car, you are moving inside the car, you observe that it looks as if the trees are moving when you are inside the car, but you inside the car, you are not moving, but you observe that the trees are moving. And even the car does not look like it's not moving inside. That means the car possesses a form of inertia, which is known as rest inertia. So talk about rest inertia, and so there's rest inertia when you are in a car, you see all that happening and all that. Then what happens when you are in a car and maybe the person just matches the brake when the car is moving? It means that you have opposed motion, and that process or that state is the inertia of motion. So we can have inertia of motion. So we can have two types of inertia. We have the rest inertia, we have the inertia of motion. So this has to, the body at rest will remain at rest, the body in motion will remain in motion unless it's acted upon by an external force, and this external force can be called friction. Then we have the second law. This is the first law, and I have the first law. We have the second law, which states that the rate of change of momentum with time is directly proportional to the force. So we can say that this force is directly proportional to the rate of change of momentum with time. Rate of change of momentum with time. So the rate of change, you can see the force is directly proportional to the rate of change of momentum with time. If you are hearing rate of change, you know that there's always definitely going to be a change, because at this point we said that momentum is equal to mass times velocity, so that's mv. So we came here now, force is directly proportional to mv minus u over t. Now in this case, every time we have a variation sign, we definitely need to remove this variation by introducing a constant of proportionality, which is f is equal to kmv minus u over t. And if you do this, you just take note that k is equal to 1. So that means f is equal to mv minus u over t. Now take note that this formula is just the same formula that we used to know as force, because we once used to know that force is equal to mass times acceleration. But the thing is that this a here was now replaced. So remember, we have 4 equations of motion. We have the 4 equations. We have the first one, which is v equal to u plus at. We have the one that is s equal to ut plus half at square. We have the next one, which is v square equal to u square plus 2as. We have the next one, which is s equal to u plus v over 2 times t. So in this part that we have a and a, we can make a subject. Let's just make a subject in the first one, in which we have v equal to u plus at. Now if we make a subject, no, this is plus, so we take this u to this side, we have v minus u is equal to at. Now if v minus u equal to at, we have that v minus u, divide both sides by t, we get a. Divide both sides by t, we get a. So a equal to v minus u over t. So at this point where you have force equal to mass times acceleration, we just replace this a with v minus u over t. V minus u over t. And that's how we got that force equal to mv u minus v minus u over t. Also at this point where we have v square equal to u square plus 2as, v square equal to u square plus 2as. All you just do is bring this u square here, have v square minus u square is equal to 2as. And we have that v square minus u square over 2s, yes, over 2s is equal to a. So we can also change this formula to be f is equal to m v square minus u square over 2s. So these are the two formulas when we are relating momentum. Then also take note that we have already existing that force is equal to mv minus u over t. So we can also relate it that ft is equal to mv minus u. So we can also say that impulse is equal to mv minus u. But when we divide by time, we now have that force equal to this. So we have this. Now we have the second law, which we just stated now, where we said the force is the rate of change of momentum with time is inverse to rate of change of momentum with time is directly proportional to the force. While the last law, the third one, which says that action and reaction are equal and opposite. Action and reaction are equal or opposite. So for every action, that's maybe for example weight acts downwards, reaction acts what? Upwards. So we have weight here acting downwards, we have reaction acting what? Upwards. So all these are what? This is the third law. The third law which states that action and reaction are equal and opposite. So take note of this. Now with all this, we've talked about the first, second and third law. We'll be entering collision as the law of conservation of mass, law of conservation of momentum, law of conservation of momentum. Now under the law of conservation of momentum, I will say that this law states that the total momentum of a closed system is always conserved. So in the total momentum of a closed system is always conserved. Now take note that total momentum before collision is equal to total momentum after collision. So total momentum before collision is equal to total momentum after collision. So take note of this: total momentum before collision or total momentum after collision. So that's it. So we are going to be entering the two types of collision. We have the elastic and we have the inelastic. Now in this elastic, it's just like seeing these two pens, they come together. So one comes to collide with this. But after colliding with this, you see they separate from each other. These two come collide. After they collide, these two pens separate from each other. What do you call that type of collision? Elastic collision. So we can say body A, this body A, collide with body B. This one with his own mass 1 and U1, collides with mass 2 and U2. You can say this is U2. Then produces another mass 1 with V1, then mass 2 with V2. So you see it. So they both collide and they separate from each other. That's what occurs under elastic collision. So you see these two pens again. So one comes, collides with this, and they both separate. So they don't stick together. You understand? And what happens is that the velocity they possess is usually far bigger and far greater than the other types. So you take note of this, that they collide and they separate from each other. But for inelastic, this is the first mass, the second mass, they collide. This one, M1, M2, they collide with each other, and U1, U2. But what happens is that they come and they collide, they stick together, and then we have M1, M2. Okay, you have M1, M2, and they possess V. So we have M1, M2, U1, U2, V, M1, M2. So we take note. So in this first one, now this elastic, under this elastic, we have that M1, U1 plus M2, U2 is equal to M1, V1 plus M2, V2. And in elastic collision, we have M1, U1 plus M2, U2 is equal to M1 plus M2 open bracket V. So in the elastic, two pens come together, they collide, they separate. But in inelastic collision, they come together, they collide, but they stick together and they move together. Now the velocity that they possess is now relative to each other. They are the same, and they don't possess as much velocity as the elastic collision. So take note that the velocity that the elastic possesses is far more than the inelastic, because this has to do with connection between them. So inelastic, you see that they come together, they come here, but what now happens is that they stick together and they possess one velocity. These two, they have different velocities, different initial velocity and a different final velocity. So U is initial vel, V is final velocity. So take note, initial velocity, final velocity. And with this, we can now go to interaction with guns and bullets. Now, under interactions with guns and bullets, we take note that if this were to be a gun, for example, see, let's take this to be a gun now, for example. Now, this gun is at rest, okay? So, we've not shot it. As far as we have not shot it, what do you think? The initial velocity is 0. The gun has its mass, the bullet has its mass. As they both possess their mass, they are both at rest, so their initial velocity is 0. But now when we shoot the gun, the bullet goes forward. But the gun possesses a form of recoil velocity. It possesses a form of recoil velocity, and that recoil velocity is negative. So take note that total momentum, let me just put the total momentum MTM before collision is equal to total momentum after collision. So total momentum before collision is equal to total momentum after collision. So if we are talking about total momentum before collision, it's equal to M1. Now, when we are dealing with mass of bullets, we're dealing with mass of gun, we're dealing with velocity of bullets, dealing with velocity of gun, they are both different. So what's supposed to be here is MB VB MGVG. Now this MBVB, now at this point, because it is initial, we will have that VB is 0, MB times 0 plus MG times 0 times 0, because it's 0 is initial, so that's why before it is what? 0. So we have that total momentum before collision is usually 0. Then total momentum after collision. Total momentum after collision. Is equal to MBVB minus MGVG. So we said the bullet total momentum before total momentum has to do with after collision has to do with MBVB, where I said the bullet goes forward. The bullet, the velocity goes forward. The mass of the bullet is positive, while for the gun is backward. That means it's negative, and that's why we have this minus MGVG. So we know that total momentum before is equal to total momentum after. Is equal to total momentum after. And that's why we will now relate this MPVB minus MGVG is equal to 0. So from here we have that MPVB is equal to MGVG. MBVB is equal to MBVB is equal to MGVG. Mass of gun, mass bullet of gun, velocity of bullets of bullets. So take note. At this point, we now have MBVB equal to MGVG. So relate them together, we'll be able to get this from that. So take note that this place that you have the VG that is minus, what we call this is also known as the recoil velocity. So take note that also known as the recoil velocity. Okay.